All right, so this is section 3.4. This is a continuation of what we talked about in section 3.3, which was the identity for cosine of the sum of two angles. And remember that it's not this guy here, cosine alpha plus cosine beta. And in fact, almost for no functions does this kind of breakdown work. In fact, we have to work pretty hard actually to figure out that this is actually equal to cosine alpha cosine beta minus sine alpha sine beta. All right. I guess we didn't actually work hard because I just gave the identity to you last time. Because if we wanted to explain it at this moment, you would have to work hard, which is why we're delaying the explanation for this until later on in the class when we can kind of give a better explanation using kind of more high-tech mathematics that we'll learn in the future. All right. So the continuation of this is the natural question. We know, how to do the cosine of the sum of two angles. What about the sine of the sum of two angles? All right. And again, it's definitely not equal to sine of alpha plus sine of beta. And again, that's almost never true, no matter what function we're talking about. And so, of course, you naturally want to ask sine of alpha plus beta, is there some sort of nice identity which tells us how to actually compute this? And in fact, there is, similar to the one for cosine. And that's what we're going to try to get right now. The good news is that this one we're going to be able to explain because we're just going to get it directly from the identity from cosine, identity for cosine. So ultimately, we'll have in this section an identity for cosine, which we got last time, an identity for sine, which we're going to do in just a couple seconds. And we'll also write down the identity for tangent, which we'll get from the identity for sine and cosine. So by the end of this section, we'll have identities for all three of those trig functions, with only the one for cosine that's unexplained. All right. Oh, by the way, for a general function, actually, just f of x plus y, there is no identity at all to even explain, to even break it down into something normal, something simple. So even though the identities for cosine are kind of ugly and kind of complicated, and the identity for sine is kind of ugly and complicated, it's almost in a way like a miracle that there are identities, period. All right, so we should be happy that there even is something which allows us to simplify these quantities. All right, so let's actually get down to it and talk about the identity for sine. So sine of alpha plus beta. We want to figure out how to break this down in terms of sine and cosines of smaller pieces. In other words, sine of alpha, sine of betas, cosine alphas, cosine betas. And the trick here is something we talked about quite a while back, and that's that we can actually write sine in terms of cosine. We can actually see this by looking at the graphs, right? So sine looks like this. This is sine of x. And cosine looks like this. And we said that the graph of sine and the graph of cosine are super related, right? They're all these humps just kind of arranged slightly differently. And in particular, you can see what I mean by arranged differently is that if we take the graph of cosine and we shift it to the right by pi over 2, then that ends up literally looking like the graph for sine. All right? So what happens is this point right there gets moved to the origin, right? And so you end up with exactly starting at the origin, a hump like that, right? Which is exactly what which is exactly what sine is supposed to be. Okay, so we know that sine is cosine shifted to the right by pi over 2. And we know from our graphing section that that means sine is cosine of whatever, right? Whatever input. And then to shift to the right by pi over 2, you subtract pi over 2, right? Replace x with x minus pi over 2. That shifts you to the right. Okay, so sine is equal to cosine of alpha plus beta minus pi over 2. Okay, the reason why we want to do this is because we know that there's an identity for cosine, and so we're just going to use that. And the problem is, of course, we have three things here. So what we can do is we can, well, you can use the identity that you found on the homework from last week and just plug them in, and immediately you'll pop out the identity that we're looking for today. Maybe if you did that problem correctly last week, try it right now, right? Just pause the video and try it right now and see if you get see what identity you get, and then you can compare it to the identity that I'm going to get right now. I'm going to do it in a slightly different way. I'm just going to do it directly from this guy up here. All right. But again, it's probably a good idea for you to plug in what you did last week in the from the paper homework. Okay. But the point of view I'm going to take is going to be like this. This is equal to cosine of alpha plus, and then I'm going to group the beta minus pi over 2 into a single entity, so that essentially the way I'm looking at this is cosine of one thing plus a second thing, right? And the cosine identity that we know tells me that if I have cosine of one thing plus a second thing, I can break that down into cosine of the first thing times cosine of the second thing minus sine of the first thing times sine of the second thing. All right. Okay. And so this is nearly what I want, right? Because this cosine alpha is nice and simple, right? It's just a single kind of input into a cosine. The sine of alpha is also nice and simple. However, we have, kind of an issue here with this cosine beta minus pi over 2 and this sine beta minus pi over 2. Not as simple as I would like. So what I'm going to do is I'm going to analyze this a little bit. One thing you could do at this point is to use the cosine identity here to resolve this cosine beta minus pi over 2, the same identity again. But the problem is you're not going to be able to do that with the sine because we don't know what the identity for sine is at right now, right? We're actually trying to figure it out. So the point of view I'm going to take is, again, looking at the pictures. So what is cosine beta minus pi over 2? That's cosine. Again, we actually just talked about this. Cosine beta minus pi over 2 is cosine of is the cosine function where you replace x with x minus pi over 2, right? So you're shifting cosine to the right by pi over 2. And again, if you look at the picture, right, this is literally the same thing that we just talked about. If you shift this thing to the right by pi over 2, you're going to get sine, right? So this this term here, the cosine alpha, stays the same. This cosine beta minus pi over 2 is sine of beta. Okay. All right, the sine of alpha stays the same, and this second kind of ugly term, sine of beta minus pi over 2, well, what is that? That's the sine function, except you're replacing the input by input beta by beta minus pi over 2, which means you're shifting the sine function to the right by pi over 2. Okay, so the sine function is up here, right? We drew it up here. If I shift that to the right by pi over 2, that's going to be this guy right there, right? This kind of negative hump right there gets shifted to the right until it hits the origin, right? So that's pi over 2. And so you end up with a hump that looks like that, all right? So it goes up like that, this red curve here. Now, what is that? Well, this is a hump that is upside down compared to the cosine hump, right? The cosine hump, let me draw it down here just because that's getting a little messy. The cosine hump looks like this, right, with at the origin, and the hump that we have looks like that, right? So it's directly upside down, right, flipped across the x-axis. And so what that means is this sine beta minus pi over 2, which is this graph down here, is the same as the cosine graph up there, except flipped upside down, which means it's negative of the cosine graph. All right, so this is actually times minus cosine of beta. All right. Okay, well, we've got two minus signs, and so cleaning this up, this becomes cosine alpha, sine of beta, plus sine of alpha, cosine of beta. All right, and that's it. That's what we're looking for. we've now broken down sine of alpha plus beta into each of these pieces, which are nice and simple, right? Cosines of alphas and betas, sines of alphas and betas. And this is the identity that we're looking for. If you do look in a book, the way the book writes it is sine of alpha cosine of beta plus cosine of alpha sine of beta. But of course, this is literally the same thing, except they've written it so that these two guys go first. So that the ordering is slightly different, right? But of course, that's the same because adding, in terms of ordering, adding doesn't care about the order, all right? So the way you remember this is you're doing cosine of the first guy, sine of the second guy, and then you swap terms, right? Sine of the first guy and then cosine of the second guy. And then how do you put them together? It's a plus, all right? Okay. So in a way, if you kind of understand our graphing section and you know the cosine identity, then you immediately get the identity for sine. Now, we're going to be using these identities quite a bit, so hopefully you'll be able to kind of automatically remember these just from working with them so much. All right, so in terms of applications, I'm not going to talk too much about them because they're actually the same applications that we saw in the last section with cosine alpha plus beta. You can, at this point, do stuff like sine of 7 pi over 12, right? Because 7 pi over 12, we saw last week, you can break it down into 4 pi over 12 plus 3 pi over 12, right? And the important point here is that 4 pi over 12 is something that we're very comfortable with. It's pi over 3. And 3 pi over 12 is something we're very comfortable with as well. That's pi over 4, right? And so you end up with sine of pi over 3 plus pi over 4. And each of those, right, we know the sines and cosines of. We know sine of pi over 3. We know cosine of pi over 3. We know sine of pi over 4. We know cosine of pi over 4. And so that means we can apply our newfound identity to immediately get sine of 7 pi over 12. Sorry, this looks really weird. That's a 7 right there. Okay, so let me actually do that. Let me just copy down. I'm just going to use the identity written the way the book does it. So this is sine of the first guy, so sine of pi over 3, times cosine of the second guy, and then plus, and then you swap terms, cosine of the first guy, and then times sine of the second guy. All right. And again, the really important point is we know every one of these individual pieces. Sine of pi over 3 is root 3 over 2. Cosine pi over 4 is root 2 over 2. And then cosine pi over 3 is 1/2. Sine of pi over 4 is root 2 over 2. So we end up with root 6 plus root 2 all over 4. Okay, so pretty much the same application that we saw last week, except with sine in place of cosine, and the sine identity in place of the cosine identity. All right, another set of problems that we could do are ones relating to verify, right? Now, at this point, you'll find verify problems in this section. And now you have in your arsenal the sine identity. So you might need to use the sine identity to verify equations in addition to all the other identities that we've talked about. Okay. So all the examples that we talked about last time in terms of adding angles apply. So again, we have a much bigger arsenal of angles that we can now compute, right? So sine of 7 pi over 12, just before 5 minutes ago, right, you wouldn't have been able to calculate it. Okay, let's see. What did we do last time with cosine? After we got the cosine identity, cosine of alpha plus beta, we talked about cosine of alpha minus beta, and we can do the same thing here. So what's sine of alpha minus beta, right? So that's a natural question to ask. And again, we're going to answer it in the same way we did it with the cosine last week. We're going to think of this as sine of alpha plus negative beta. right? And the reason we're writing it this way is because just now we figured out an identity for sine of something plus something else. And we're just going to apply that identity, and then we'll deal with the negative sign after we've written down the identity. So this is equal to, and now I'm just again quoting the identity. Let me scroll up again. So right there, right, plus. So this is going to be sine of the first guy, cosine of the second guy, plus cosine of the first guy, sine of the second guy. All right. Okay. This looks okay, but we still have some ugliness here. We have this minus sign there and that minus sign there, which luckily enough we can clear up because we know about the odd and evenness of sine and cosine, right? We know cosine is even, so cosine of minus beta is the same as cosine of beta. So this is sine of alpha, cosine of beta. We know sine is odd, so sine of minus beta is minus of sine beta. So the minus sign we can bring out to here, cosine of alpha, sine of beta. All right. So this is going to be, so first of all, this is nice and clean now, right? Just we have sine of alpha, cosine beta, cosine alpha, sine beta, all very simple terms. And now we've essentially broken down this sine of alpha minus beta into really, really simple pieces. Okay, and notice, of course, the big difference between sine of alpha plus beta and sine of alpha minus beta is the minus sign right there. Okay, so just like last week, last week, the difference equation or difference identity for cosine allowed us to calculate stuff like cosine of pi over 12, right? So now we're going to be able to calculate sine of pi over 12, right? And the point of view here is that sine of pi over 12 is sine of pi over 3 minus pi over 4, right? And that makes sense because if I actually did common denominators here, this is pi over 3 is 4 pi over 12, and pi over 4 is 3 pi over 12. And so when I subtract them, I get pi over 12. Okay. And so we can just use our identity to break this down into simpler pieces. This is sine of pi over 3, cosine of pi over 4, and then minus cosine of the first guy, pi over 3, and then sine of the second guy, pi over 4. All right. And ultimately, we're going to end up with sine of pi over 3, which is root 3 over 2. And then we got root 2 over 2 minus 1/2, and then root 2 over 2. And that ends up giving us root 6 minus root 2 all over 4. Okay. All right, so again, the same kinds of applications that we saw last week, except with sine replaced with cosine, sine identity replaced with the cosine identity. One thing to note about this, the difference identities, I think I said this last week for cosine as well. You never really have to memorize this one because you can just use the sine A plus B or sine alpha plus beta and just remember to break it up in this way. And you can reproduce the A minus B, the alpha minus beta identity immediately. So if you're kind of bad at memorization, which I am, just remember how to reproduce the formula from the sine alpha plus beta formula. All right. Okay, but probably what will happen is in this class you'll be using it so much that you'll kind of automatically have it committed to memory. All right, and again, this allows us to also do verify problems that involve, sine of something minus something else. Okay. Let's see. So those are two situations for sine and cosine. The next natural question is to ask, well, can I do the same thing with tangent? Right? And the answer is yes. And this one is actually very straightforward, right? The one for sine that we got from cosine was a little tricky, right? We had to kind of understand the graph of sine and cosine. we had to kind of use a little trick by grouping the beta and the minus pi over 2 together. So it was still slightly sneaky, but this one is very, very straightforward. Tangent alpha plus beta, I'm just going to write as sine of alpha plus beta over cosine of alpha plus beta. Literally, that's the definition of tangent. And then I'm just going to directly quote my identities for sine and cosine. So my identity for sine that we just got, right? Sine of alpha, cosine of beta, plus cosine of alpha, sine of beta, over, and then I'm going to use the identity for cosine, cosine alpha, cosine beta, minus sine alpha, sine beta. Okay. Now, this is, in practice, this is probably good enough to use in that we have broken down tangent of alpha plus beta, which is very complicated, right, into easier pieces, just sine alphas and cosine betas and so on. But there's an alternate way we can express this, which maybe looks a little cleaner. And the way we're going to do that is we're going to notice if I multiply this expression here on the top and the bottom by 1 over cosine alpha cosine beta on top, and then of course the same thing on the bottom, 1 over cosine alpha cosine beta on the bottom, then what's going to happen is I'm going to get, first of all, a lot of cancellations. So you can see this cosine alpha down here is going to cancel a bit with that cosine alpha here, and so on. But also, this cosine alpha down here is going to interact with that sine alpha up there and give me a tangent, right? So even though this looks a little weird, what's going to happen is I'm going to expect a lot of cancellations, so a lot of ones, and then a lot of sine alpha over cosine alphas, or sine betas over cosine betas, which turn into tangents. And ultimately, this is going to give me something kind of simple. So let me do this. So let me emphasize that I'm multiplying these two guys to the entire expression on the top, entire expression on the bottom, right? And so we need to actually distribute this 1 over cosine alpha cosine beta to both terms, right? And same thing on the bottom. And so when I do this distributing on the top, when I multiply sine alpha cosine beta to 1 over cos alpha cos beta, let's see, the sine alpha over cosine alpha is going to end up, actually, let me write this out carefully just in all the pieces, and then I'll do the cancellations. So everything perhaps is more clear. So I'm just going to distribute everything in and then do the simplifications afterwards. So cosine alpha sine beta over cosine alpha cosine beta, right? And then on the bottom, cosine alpha cosine beta over cosine alpha cosine beta. And so you can see this is going to be a really nice and simple term. Sine alpha sine beta over cos alpha cos beta. All right, so let's look at all the cancellations here. The easiest one here, cosine alpha, cosine beta, cosine alpha, then cosine beta cancels with cosine beta. Let's see, upstairs we've got cosine beta and cosine beta canceling. Let's see, to the right here, we've got cosine alpha and cosine alpha canceling. And down here we have nothing canceling, all right? However, sine alpha over cosine alpha for this first term is tangent. So that's tangent alpha. The second term, sine beta over cosine beta, is tangent beta. On the bottom, that's just a 1 because everything cancels away. And to the right, bottom right here, we have sine alpha over cosine alpha, which is tangent alpha. And then sine beta over cosine beta, which is tangent beta. And so even though, in our first step over here, kind of that's already pretty much usable, our very last step, it looks very nice because we've broken down tangent alpha plus beta in terms of all tangents, right? Tangent alphas and tangent betas. So that makes a very nice looking identity, very clean looking, all right? Okay, in terms of applications, of course, all the same applications apply, right? So we know tangent of alpha plus beta has a nice formula. And so therefore we automatically know, right, tangent of pi over 3 plus pi over 6, right? Whatever that is, because we know tangent pi over 3's and we know tangent pi over 6's. Okay, so this one is easy, and let me put that in quotes. And of course, what I mean by easy is that we have a nice formula up there. Okay. All right, maybe a fun exercise for you, I'm not going to write it down, is to figure out what tangent of alpha minus beta is, right? Find this formula. And that's a nice exercise to see if, kind of you understood what we did, the corresponding thing that we did for sine and cosines, all right? The tangent formula is not nearly as important as the ones for sine and cosine, so I'm not going to dwell on it very much. But again, at this point, you'll see you'll be able to see verify problems that involve tangent. All right. Let's see. So that's pretty much it for this section. Maybe a fun exercise for you to see if you're comfortable with this is to try the same thing. What's cotangent of alpha plus beta? Can you figure out a nice formula for it? Can you actually write it in a nice way, just like we wrote the tangent identity in a very nice way? All right. So you do this. But of course, this is not one that absolutely not. You should not memorize the cotangent one because, well, for our class, we'll probably pretty much never see it again. But, just figuring it out is probably very good for you. Kind of reproducing it is very good for you in terms of understanding the ones that we actually care about. All right. So actually, that's pretty much it for 3.4. 3.5 is where we're going to talk about some more identities, but they're going to be, in a way, more interesting than the ones we've talked about here, because the ones here were simply, in a way, extensions of the cosine identity.